From the previous video, we used the linear regression to demonstrate various gradient descent algorithms. In this video, we will build upon the linear regression and explore polynomial regression. Then, we will use another technique called learning curve to understand model overfitting or underfitting. Let's get started. If our data is more complex than a straight line, how can we find the best fit model? We can still use a linear model to fit nonlinear data. For example, our data follows the function y equals 2.5 times x squared plus x plus 2. How can we fit this function with the linear model? It is actually quite simple. We can rewrite the function in a linear form. Y equals 2.5 times x2 plus x1 plus 2 times x0. Here, we treat x2 as an addition feature, which can be computed as x1 squared. This is called polynomial regression. It allows us to use linear regression model to generate polynomial regression. Let's jump into the code and test it out. Like the previous video, we randomly initialize 100 values for x between 0 and 1, multiplying by 6 and subtracts 3. The calculation shifts x in between -3 to 3. This is how the data points looks like. The polynomial features function calculates x squared for us. For example, if the first dataset value is -0.75, its square is approximately 0.56. The linear model function automatically quits the bias term, so we leave the bias term parameter as false. After transforming our input x into polynomial features, we can fit it into a linear regression model. Due to the random noise, we can't get the original theta values 2, 1, and 0.5, but these are pretty close. In our example, we have only one feature, x. If we add another feature, x2, the polynomial features function will transform the features to include all features combinations. Now, we know how to use linear regression to calculate polynomial regression. Let's move to the next topic, learning curve. In this graph, the green line represents a 300-degree polynomial model that fits the training data, while the red line represents a 1-degree polynomial model. The 300-degree polynomial is clearly overfitting, and the 1-degree polynomial is underfitting. In this example, we know the data was generated using a quadratic function, so it is easy to recognize overfitting and underfitting. However, in real-world scenarios, how can we determine whether a model is overfitting or underfitting? If you recall chapter 2, initially, we fit a linear model to the housing data, which resulted in a poor training and validation score. That was an example of underfitting. Then we used a random forest model, which achieved zero error on the training set, but performed poorly on the validation set. That was an example of overfitting. In general, if a model performs poorly on both training and validation sets, it is underfitting. If the model performs well on the training set, but poorly on the validation set, it is overfitting. A learning curve provides a visualization way to analyze underfitting and overfitting. Learning curve functions helps us to draw the training error and the validation error. We will continue to use the same x and y values from our previous example. The function splits the data into 80% training and 20% validation. In our case, 80 values of x are used for training and 20 are used for validation. The model trains 40 times, each time using a larger portion of the training data. This allows us to observe the training and validation error changes as we increase the training data size. For a linear regression model, the training error spikes and then reach a plateau. The training and validation errors converge at a similar RMSE. Because linear regression is underfitting, it struggles to fit the training set, leading to large errors on both training and validation sets. For the polynomial model, we simply replace the linear regression with polynomial regression. The resulting graph looks different. The training error is lower than before, but there is a gap between the training and validation errors. When overfitting occurs, the model fits every data point in the training set but fails to generate well to unseen data. Now we have learned another tool to assessing underfitting and overfitting. Let's introduce three key terms related to the model generalization error. First, bias. Bias refers to incorrect assumptions in a learning algorithm. A high bias model underfits the training set. Second, variance. Variance measures a model sensitive to the small fluctuation in the training set. A high variance model overfits the training data. Third, irreducible error. This is a part of error that it is inherited in the dataset due to the noise. The only way to reduce it is to clean up the data. This is the end of this video. Thanks for watching. If you found this video interesting or learned something, please consider like and subscribe. See you in the next video.